So we've been given a function, f of x is equal to x over x squared plus 4. I'm interested in finding the intervals of increase and decrease, as well as the intervals of concavity. So for intervals of increase and decrease, this is where we are going to be analyzing the first derivative. So let's go ahead and start by taking a derivative. To take this derivative, we're going to need the quotient rule, one of my favorite rules for derivatives, as my students will tell you. This will be low, d high, derivative of x is 1, less high, d low, derivative of x squared plus 4 will be 2x, over the square of what's below. Simplifying this numerator as much as possible, we'll get x squared plus 4. The 1 doesn't do anything. Minus x squared all over. X squared plus 4. Quantity squared. Continuing to combine like terms, we'll call this 4 minus x squared over x squared plus 4 quantity squared. Now, because the denominator cannot be factored and is always positive, we don't need to worry about critical values in the form of f prime does not exist. Rather, we can set the numerator equal to 0. Now, what I frequently say at parties when I go to parties is that a difference of perfect squares factors into binomial conjugates. I know you guys can't see it, but I think you know what I just did. 2 plus x and 2 minus x for 0. So x is going to be equal to plus or minus 2. So like we did on our other examples, we'll set up a couple of intervals, -2, +2, and that gives us a total of 3 test intervals, -infinity to -2, -2 to +2, and +2 to positive infinity. For -infinity to -2, I'm going to plug in x equals -3. I'm going to plug it into this form of the first derivative. So f prime of -3 is going to be equal to 4 minus -3 quantity squared over, oh boy, -3 squared plus 4 quantity squared. Your numerator is 4 minus 9. Numerator is negative. Your denominator is being squared, so it's always positive. We can conclude that this will be an interval of decrease due to the fact that we got a negative for our final answer. Let's see if we can leave a little more room on this one. For -2 to +2, for this one I'm going to test x equals 0. So f prime of 0 is going to be equal to 4 minus 0 squared over 0 squared plus 4 quantity squared. Your numerator is 4 minus 0, that is positive. Your denominator is 0 squared plus 4 quantity squared. Your denominator is positive as well. Positive divided by positive is positive, therefore -2 to +2 is going to be an interval of increase. Finally, for 2 to infinity, this time we'll pick x equals 3. Nice boring number. Nothing wrong with being a little boring in a math class from time to time. This will be 4 minus 3 squared over 3 squared plus 4 quantity squared. Your numerator is -5. Your denominator is something squared. That'll be positive. Negative divided by positive will be negative, telling me that 2 to infinity is an interval of decrease. Good, so that takes care of the intervals of decrease. So what we just got is that the original function will be decreasing up until -2, where it will then increase until we get to +2, where it will continue to decrease once again. Now, what I'm going to describe is called the first derivative test, where you can use the first derivative to classify your critical values as local maxima or local minima. If we change from decreasing to increasing, what kind of local extreme point would that give? Well, that's going to be a local minimum. Whereas if we change from increasing to decreasing, that is going to be a local maximum. So change from decreasing to increasing, local minimum. Change from increasing to decreasing, local maximum. Now, what we're going to do is check the concavity as well and see if what we get for the concavity is consistent with what we see up here. Because it looks like it starts off concave up and then it's concave down for a little while. So for intervals of concavity, we're going to reproduce what we just did. We're just going to do it with a second derivative instead of a first. So we already got that f prime of x is equal to 4 minus x squared over x squared plus 4 quantity squared. I'm going to apply the quotient rule again. So quotient rule says we're going to have low, d high, derivative of the top is going to be negative 2x, less high, d low. Now this one's going to be a little bit more complicated because we have a composition of functions, so we'll need to make use of the chain rule. So we'll start with the derivative of something squared, which will be 2 times that thing to the first power. Then the chain rule says multiply by the derivative of the inside. That'll be times 2x. This is all over what's below squared. Now it was already squared though, so we're going to square it again. With that in mind, I'm not going to simplify too much in the numerator, but I am going to pull out this common x squared plus 4 that we have to both of the terms in the numerator. So pull out an x squared plus 4. Now we'll use stronger brackets this time. The first term will be negative 2x times the remaining x squared plus 4. The second term, I just factored this part out, so we'll still have minus 4 minus x squared times 2 times 2x. So that'll be times 4x. Over the square of what's below. Now when I square the square, we multiply the exponents to give 4th power. We can then cancel out the one of these that we just factored out from the numerator with one of these in the denominator and take it down to the 3rd power. I still need to continue to simplify the numerator though. So I'm going to distribute the negative 2x through to both of these terms. We'll get negative 2x cubed minus 8x. Distributing the minus sign and the 4x, we will get minus 16x and then plus 4x squared. I'm going to simplify that over here to the right. No, that's not 4x squared. That'd be 4x cubed. There we go. That's how we fix a 2 into a 3. Perfect. So we got 4x cubed minus 2x cubed. That will be 2x cubed. Minus 8x minus 16x will be minus 24x. Now, same as our previous case, our denominator is never going to be equal to 0, so we don't need to worry about that as a critical value. Instead, what we'll do is pull up a new sheet and recopy what we just got for this. So the second derivative will be equal to 0 if 2x cubed minus 24x is equal to 0. That'll give us our endpoints for our test intervals. So with that in mind, we can pull out a greatest common factor of 2x, leaving us with x squared minus 12. This doesn't factor in binomial conjugates too well, so we'll apply the zero factor property and say that one of these two things will have to be true. Either 2x is equal to 0 or x squared minus 12 is equal to 0. First one, we simply divide both sides by 2. Second one, we'll move the 12 over to the other side and then take a square root of both sides. 12 factors into a 4 and a 3, which means that the simplified radical will be 2 square roots of 3. Now what this tells me is I am going to have a total of 4 test intervals with cutoffs at negative 2 square roots of 3, 0, 2 square roots of 3. So my 4 intervals are negative infinity to negative 2 square roots of 3, negative 2 square roots of 3 to 0, 0 to 2 square roots of 3, and then 2 square roots of 3 up to positive infinity. I want to test all of these intervals, and we will be plugging them back into our first derivative that we got back here. You know what, why don't I go ahead and recopy that so that we don't have to keep referencing back to it. 2x cubed minus 24x all over x squared plus 4 quantity cubed. Cool. So that's where I'll be plugging these things in. So to test negative infinity to negative 2 square roots 3, I would like to use the number. So negative 2 square roots of 3 is about negative 3.5. So let's go with x equals negative 10 just to be sure. So f double prime of negative 10 is going to be 2 times negative 10, quantity cubed, minus 24 times negative 10. This is all over negative 10 squared plus 4 cubed. This number is negative 1,000, multiply by 2, we get negative 2,000. Then we're going to add 240 to that. That is still going to be delightfully negative. Your denominator is 104 cubed. As much fun as that sounds to do in my head. Nah, I'll leave it for later. Negative up top, positive on the bottom lets me know that this interval we get a negative value. As a result, we are able to conclude on this interval that the function is concave down. We'll use CD for concave down. For the next interval, negative 2 square roots of 3 all the way to 0. Again, negative 2 square roots of 3 is about negative 3.5, so I'm going to use x equals negative 1 just to be sure. F double prime of negative 1 is going to be equal to 2 times negative 1, quantity cubed, minus 24 times negative 1, all over negative 1 squared plus 4, quantity cubed. This is negative 1, multiply by 2, we get negative 2, plus 24, that's going to be positive 22. Your numerator is denominator is 5 cubed. That's 125. That one I can do in my head. Regardless, we get a positive value, letting us know that this interval is going to be concave up. Good. For 0 to 2 square roots of 3, this will look very similar to the last one. We'll use x equals positive 1. Really, the only thing that's going to change for this function is we'll get rid of some negatives. This will be 2 times 1 cubed minus 24 times positive 1, all over 1 cubed plus 4, 1 squared, plus 4, quantity cubed. Now, word to the wise, if you square 1 and cube 1, you might get radically different results. If that happens, recheck your work. Your numerator will be negative 22. Your denominator will be positive 125. You are getting a negative value for this, letting you know on this interval we are concave down. You may have noticed a pattern, but we're going to go for it anyway. For 2 square roots of 3, all the way up to positive infinity, I'm going to say let's go with x equals 420. And we're going to be plugging in f double prime of 420. This is going to be equal to 2 times 420, quantity cubed, minus 24 times 420. All over 420 squared plus 4, quantity cubed. I don't know what these two numbers are, but I know that 420 cubed is way bigger than 24 times 420, so that's going to be a positive numerator. Positive numerator, positive denominator means that we have a positive value. So with that in mind, on this interval, we are concave up. So to summarize all of the things that we just found, let's grab the back of this piece of paper. The original function was f of x is equal to x over x squared plus 4. So the intervals of increase, we got that this thing was increasing on, increasing on negative 2 to positive 2, and it was decreasing everywhere else. So it was from negative infinity to negative 2. You can use a union, or you can use a comma to separate them, 2 to infinity. Then we got concave up on the following intervals. Concave up was from negative 2 square roots of 3 to 0, as well as 2 square roots of 3 to infinity. And then we have concave down on negative infinity to negative 2 square roots of 3, as well as 0 to 2 square roots of 3. If you need to check back in the video to get what any of those intervals were, please feel free to rewind and rewatch.